Alright, let's take a look at solving problems in cylindrical coordinates. So, you've used these before. Cylindrical coordinate would be maybe locating at some angle theta, some distance r, and some angle z, or some distance z. Let's just look at the x and y plane for right now. We have a path that's curvilinear. We're still in the curvilinear section. And we can identify the position at any given time by some vector r. Alright, that vector r is also defined by some angle theta. So we're just looking in the xy plane. On this path, we can say that it has some unit r direction. I'll go over that in a second, and some unit theta direction. Okay, so we don't necessarily solve problems in cylindrical coordinates because it's shaped like a cylinder. We solve problems in cylindrical coordinates because r can change with time and theta can change with time. So if you imagine r changing with time, this could be something like a piston extending. Well, if that piston extended while you swung it through some angle theta, then you would have cylindrical motion. So this would give us some acceleration like that. We always have a velocity vector tangent to the path, and let's figure out how to find those velocities and accelerations. Okay, so go ahead and remember, if we have something in 360 degrees, we can say that's equal to 2 pi radians. And you can also use the conversion factor. 180 is equal to pi radians. For a real quick example, if you had 260 degrees, you want to cancel the degrees, so 180 degrees on the bottom, that cancels, and we end up with an answer in radians. And I'm not even sure what that number is, but that's how you do it. Okay, so I'm going to derive the velocity vector from the position vector, but once again, let's look at it real quick. The position vector at any given moment is defined by some magnitude r in the unit r direction. So it's pointing in this direction and it's r long. Okay, so I'm going to write that down. The position vector r is r long and it's in the unit r direction. I'm going to go ahead and derive velocity for you, and I'm probably going to leave the acceleration derivation up to y'all, but I may give you a point or two. Okay, this looks like we should maybe say this is some f and some g. I'm going to go ahead and do f is equal to r, f prime is equal to r dot, g would be some unit r vector. How do we take the derivative of that? Just put a dot on top of it. Okay, so putting all back together, we can get r dot, and the time derivative of this is equal to r dot in the unit r direction plus r times the unit r direction. Alright, we're not quite done yet because they're both in the same direction right now. We need to change this into a unit theta direction. This one, we could analyze the meeting right now. So think of that piston or shock moving in and out with some velocity in the radial direction, pointed in the direction of the unit vector r. That is this component right here, but we need to break up what this is just a little bit. If we say that some delta in the unit direction r is approximated by some delta theta, unit direction theta. Very, very, very close. Take a look at, I think, figure 2030. Sorry, 1230. I can't draw it probably quite as well. And I'm looking at page 72 right now. Alright, so if we make this approximation right here, we can get that the time derivative in the unit r direction would be the limit of, make the substitution, delta unit r over delta t, as delta t goes to 0. Sorry, talking faster than I can write. So there's your substitution. And we still need this unit theta that goes along with the substitution. If we remember d theta dt, or we can define this right now, that's like our omega, our angular velocity, and we're going to call it theta dot. We're going to deal with this plenty in the future. So get familiar with the terminology. Okay, and that would be a theta dot in the unit theta direction. Alright, so I get this. Okay, we can put it all back together now, and we started with r dot. Well, that's the velocity, right? In the r direction. Let's just keep calling it r dot though. When we're in cylindrical, let's use r dot and theta dot as much as possible. So we have some r dot in the unit r direction plus some r theta dot in the unit theta direction. The r came from here, if you're wondering. The theta in the unit theta direction came from right there. Okay, these are components. We can make a vector out of them. So we had some path like this. Its velocity vector would be tangent to that path, and it's gonna have a unit theta direction and some unit r direction, or may or may not, but we can find the magnitude of r dot by taking whatever the components are squared. So r dot squared plus r theta dot squared, and we can find the angle between them too.